Okay, here we are back in my office with my creaky chair, ready to begin section 2-3, deductive reasoning. So our goals for this section are to use the law of detachment and to use the law of syllogism, which of course we will define. So before we do, though, we need to define something else. We need to define deductive reasoning. Let me write this down for y'all. Deductive reasoning. So deductive reasoning, or logical reasoning, is the process of reasoning logically from given statements to a conclusion. From given statements to a conclusion. Okay, hopefully not too difficult. So we can use this in actually everyday life, probably more than most math. So let's just dive right into example 1. We'll change colors for the fun of it. Example 1. So example 1 says, an auto mechanic knows that if a car has a dead battery, the car will not start. Let me write that down. A mechanic, and I'm going to try and short it. A mechanic knows if a car has a dead battery, it won't start. Okay, so then we fast forward a little bit and say, well, then the mechanic begins working on the car. The mechanic works on a car and finds a dead battery. Okay, well, if we think logically about this, forget math for a moment. If a mechanic finds that the battery is dead in a car, some of you maybe have already taken driver's ed or started driving. Unfortunately, maybe you've experienced this. If a car's battery is dead, it definitely won't start. It needs that juice. So the mechanic finds this dead battery, and guess what? The mechanic can conclude. The conclusion, the car won't start. Hopefully it's not too difficult to see that that's just a pretty easy logical process of what we would call in math or geometry, deductive reasoning. So we can use this to then come up with something called the law of detachment. For the fun of it, again, change colors. Law of detachment. So nice fancy name for something that's pretty easy. It's saying if a conditional is true, so the if-then statement, that's the conditional, is true, and its hypothesis, the if part, is true, then the conclusion is also true. So if I look back at my example 1, for example, so here in the beginning, the burgundy part, that would be my conditional. If a car has a dead battery, I could insert here, then it won't start. So there's your conditional. That is a true conditional statement. So that's this first part of the definition. If a conditional is true. Then it says, and its hypothesis is true. So here we have a statement that happens to be the same as the hypothesis of the conditional. So the mechanic found the dead battery. Yay. So then that also is going to mean that the conclusion must be true. right here is the conclusion. The car won't start. So we can write this symbolically, and I have a little, this one right here. We'll bring this in here, scooch this up, give us some space here. So we have this is in your book on page 83. Page 83. If a conditional is true and its hypothesis is true, then its conclusion is true. In the symbolic form, we have this little thing right down here. And we read that as if P, then Q. Hopefully that looks familiar from the previous couple of sections. So if P then Q is true and P is true, then of course Q must be true if that's the statements you're given. So we can use this. Let's go ahead and use this in example 2. Example 2. For the given true statements, they're already telling us it's true, what can you conclude? Here is the given. Given. I'm going to read it and then I'm going to write it. If M is the midpoint of a segment, then it divides the segment into 2 congruent segments. I'm going to write it more slowly and say it too. If M is the midpoint of a segment, then it divides the segment into 2 congruent segments. Okay? Conditional statement is true. So then they also give us this statement. They don't label it as a statement, it's just then written below. I'm going to label as statement. So here's what they then give us. It says M is the midpoint of AB, segment AB. So I'm going to, for the fun of it, just sketch this real quick. So if we have segment like this, and it's labeled AB, and it said if M is the midpoint of a segment, so there's my segment, there's M, and then it says that it divides it into 2 congruent segments. So I can give my little tick marks on here to show that those 2 parts are congruent. So what can you conclude then? What can you conclude? Well, I can conclude that segment AM is congruent to segment MB. Okay? That's the law of detachment. So I've taken this conditional up top, the given statement, and then the statement that they gave me was that M is the midpoint. So then if that's the case, M is the midpoint, then I can jump to the conclusion. It divided the segment into 2 congruent segments, and I named them right here. Okay? If you need some extra practice with that one, there's a check understanding question right below example 2 in your book, also on page 83. I call those a try this or check understanding. It's about a baseball, so baseball player. So if you want to do it, go ahead, pause the video and try it, and the answer's in the back. I'm going to keep moving on to example 3. Example 3. So does the following argument illustrate the law of detachment? That's what I want to know here. Let's go back to, we'll use blue still. Given. So here's your conditional. If it is snowing, then the temperature is less than or equal to 32 degrees Fahrenheit. Okay? And then you conclude, oh, sorry, there was a statement there, I apologize. Let me get rid of all that. So here's your statement. The statement says this: the temperature is 20 degrees Fahrenheit. So what can you conclude? Well, let's take a look at this. I'm going to underline it with a different color here. So if it is snowing, there's my hypothesis. My conclusion is the temperature is less than or equal to 32 degrees. Okay, well, the statement that they gave me is this right here. The temperature is 20 degrees. Well, that's less than 32, but that's going to the conclusion, not to the hypothesis. It says nothing about snowing. So those of you here that live with me in Michigan, which I think is all of you, we have plenty of days in winter that are 20 degrees or less, but it doesn't guarantee that it's snowing. It just happens to be a cold day. So there's really nothing I can conclude here. Nothing to conclude. Because the statement that I was given relates to the conclusion, not the hypothesis. So there's nothing you can do here. The law of detachment only works if you're given a true conditional and then starting with its hypothesis. So this idea of if P then Q, and then your statement says P, you can conclude Q, whatever it is. You can't have, I'm going to do this in this sort of different color here. So if, it just keeps changing on me, if P, then Q, and then you're given Q as your statement, you can conclude nothing. Okay? Maybe symbolically it makes a little bit more sense. So let's move on to another idea here, the law of syllogism. I'll go with purple. Why not? Law of syllogism. So this allows you to state a conclusion. To state a conclusion from two true conditionals. So it's kind of using this somewhat the similar idea. I'm going to pull in the picture from your book. So here's your key concept of the law of syllogism. If P then Q and Q then R are true statements, then we can actually make this a little more simple. We can say if P then R is true. I like to write these two vertically. So if I say if P then Q, and then also if Q then R. Well, if I see it that way, and my train of thinking, I'm going to change colors with this for a second, goes kind of like this, like that. So I'm starting here at the P, going to Q, and then going back to Q and going to R. I can make it more simple. I can get rid of these extra Q's in here because it's just repeating itself. So I can then instead say if P, then R. So that you'll see it, I think, a little bit more clearly as we do an example. But that's the symbolic type picture, I guess you could say, of it. Let's try example 4. Example 4. Okay, use the law of syllogism to draw a conclusion from the following true statements. They're telling us again that these two statements are true. I'm going to write both of them. If a number is prime, then it does not have repeated factors. If a number is prime, then it does not have repeated factors. And for the sake of clarity, I'm going to change colors here. So the second conditional is this. If a number does not have repeated factors, then it is not a perfect square. if a number does not have repeated factors, then it is not a perfect square. Okay, so we have two true conditional statements. For the quick, just a side note, what we're talking about with factors here. So if I take a number such as 12, and I use the factor tree idea, if I say 2 times 6 is 12, and then 2 times 3, so the factors then would be 3 times 2 times 2. So right here I have a repeated factor. So if a number is prime, for example, let's just pick 11. Well, the only way I can break down 11 is 1 and 11. 1 times 11 is 11. So in the 12 example, I have a repeated factor of 2 times 2. In the 11 example, I have no repeated factors here. So if a number is prime, then it does not have repeated factors. If a number does not have repeated factors, like this one, then it's not a perfect square. 11, hopefully is obvious, is not a perfect square. If I were to pick a number like 16 and break it down, I could say 2 times 8 and 2 times 4 and then 2 times 2. So this would give me 2 times 2 times 2 times 2. It's all repeated factors. I could even say it as 4 times 4. There's my repeated factors to make 16 a perfect square. So if I keep going with these, with the blue conditional, if a number does not have repeated factors, right here, the 11, then it's not a perfect square. 11's not a perfect square. 12's not a perfect square either, though, but it's also not prime. 16 was my perfect square number, so that perfect square number, it's not prime, and it does have repeated factors. So what can I do with this whole two system conditional statements? Let's take a look at this. Here's the first hypothesis. If a number is prime, then it does not have repeated factors. It does not have repeated factors. That sounds familiar. Let's look at the second conditional. If a number does not have repeated factors, I'm keeping it purple for that reason. That's the same thing. Then I can go on to say, then it is not a perfect square. So I can omit the two purple repeated stuff and take all that's written here. And my conclusion, or simplification you could say, is this. If a number is prime, then, and I'm going to skip all the purple stuff and go on to the orange, then it is not a perfect square. And when I say it that way, hopefully it makes a lot more sense. Well, if it's a prime number, there's no way it's going to be a perfect square, because a perfect square has two identical factors. Okay? If you want extra practice again on this one, there's another check understanding on page 84. And the answer would be in the back for that one also. Let's move on to our last example, example 5. Example 5. It says, use the law of detachment for this one. And I'm going to pull this in here just because it's a little faster than writing all this out. You can choose to write this out if you want to or not. Use the law of detachment and the law of syllogism to draw conclusions from the following true statements. They're already telling us it's true. So here's the first one. If a river is more than 4,000 miles long, then it is longer than the Amazon. Okay, so the Amazon must be really long. Our second true conditional. If a river is longer than the Amazon, then it's the longest river in the world. Okay, so then we have the final statement that they're giving us. The Nile is 4,132 miles long. Ooh, okay, well, let's simplify those first two conditionals here first. If a river is more than 4,000 miles long, there's my first hypothesis. And then it is longer than the Amazon. It sounds familiar too. Oh, here, if a river is longer than the Amazon. Those are kind of the same thing, written a little differently because it's the English language. Then I can, in the second conditional, the conclusion is it's the longest river in the world. We can conclude then with just this part here that I have the little blue-green arrow to. We can then say, let's simplify it. If a river is more than 4,000 miles long, then, and I'm skipping over to the green stuff now, it is the longest river in the world. Okay, so we simplified those two conditionals to just be one conditional, and it's true because we started with two true statements. Then we have that statement, the Nile is 4,132 miles long. So take a look at this. It's kind of like that mechanic one. If a river is more than 4,000 miles long, well, it's saying that the Nile is more than 4,000 miles long. So therefore, the Nile is the longest river in the world. And for the fun of it, your book mentions that over 99% of Egypt's people live close to the Nile River. Maybe because it's a desert and they need water. Okay, so that's it. And again, if you want another problem to try with that one before jumping into your assignment, it's on page 84 again. For check understanding, the answer is in the back. Otherwise, check out your assignment, try them, let me know if you have any issues. Thanks for joining me.